మెసేజ్ ఎట్లా కొడతాం బ్రో దీంట్లో?
చాటా
స్లో.
So very good afternoon to all the participants. Kindly mute yourself. Okay. Hello. ఒక్క నిమిషం మేడం చేస్తున్నాను. ఇది మీరు కనిపించట్లేదు అక్కడ.
Okay, good afternoon, everyone. Welcome all the participants for the second session of the first day of the 5-day FDP program. on domestic and industrial water and wastewater treatment. And I welcome today's speaker, Dr. Somak Chatterjee. And I once again welcome all the participants for this session, and I request Dr. G. Srinivas, Assistant Professor, Department of Chemical Engineering, BVRIT Institute of Technology, to please take over and introduce Dr. Somak Chatterjee, who is today's speaker. Srinivas sir, please introduce.
So good afternoon to all the participants. Today I'm pleased to invite Dr. Somak Chatterjee as a keynote speaker for the second section. Okay, he was assistant professor in BVRIT Pilani Chemical Engineering Department, and he was experienced. Sorry for the inconvenience. I'm pleased to invite Dr. Somak Chatterjee sir. He was assistant professor in BVRIT Pilani Chemical Engineering Department, and assistant professor in Chemical Engineering Department BVRIT Pilani, and he was 2 years of experience as a senior scientist in BVRIT Technology Private Limited, Bangalore, and he was 1 more year experience senior engineer in Tech Mahindra Technology Center, Hyderabad, and he was handled 2 major projects, sponsored projects by BVRIT Pilani. And he has publications of about 15 with an average impact factor of 3, and he was published 1 book, and he was having 4 US patents and 1 Indian patent, and he was bagged several awards, and some of them are I'm just briefly demonstrating. Top 3 shortlisted in SCRB IGCW award of fluoride removal from groundwater using chemically amended naturally available materials 2019, IIGP 2.0 by DST Lockheed Martin by Tata Trust University Challenge Award, and he was a Pat on Back Award GE IDC Tech Mahindra Hyderabad, and also he was received Mahindra Electronic Environ Rice Award for the best product innovative, and he was several types of prototypes he was designed. Some of them are fluoride filter, lead detection, and polymeric capsules, and leak detection using conductive premier and aseptic handles for refrigerators. And he was completed and ongoing several industrial projects as a consultancy work from GE Appliances and PepsiCo, Pro Coater, and KX Technologies, and many more. Thank you, sir. Thank you for accepting our invitation as a keynote speaker. I request you to kindly proceed for further section. Thank you, sir. Sir, your voice is not audible, sir. Madam. Sir, your voice is not audible, sir. I think increase system volume, sir. Probably that may be the reason. Sir, I will be making you as a host. Kindly take the host and please mute all the participants and carry your section, sir. Yeah, yes, sir. Now it's clear, sir. Yes, sir. You can proceed, sir.
देखो
Okay, sir. Fine, sir. Fine. Sir, good morning. Good afternoon, sir. Sir, Somak Chatterjee, sir. Good afternoon, sir. Sir, good morning. Good afternoon, sir. Somak Chatterjee, sir. Good afternoon, sir. Sir, good afternoon, sir. No, sir, not audible, sir.
Well, now can you hear me?
Now we are getting, sir.
Okay. Yeah.
Yes, sir.
Okay, at last. So everyone can hear me, right? Okay. So thank you, Dr. Srinivas, for inviting me in this podium. It's an honor for me to present my research case before everyone over here. This is I'd like to share my screen for presenting the research work that I've done, and how it is relevant to the present day water treatment amidst this emergency situation that the entire country is facing of COVID-19 infection. So let me share you my screen. So, Dr. Srinivas, can you please enable to share me my screen? I cannot do it actually. Yeah, thank you. So I hope all of you are able to see my screen. Okay. Uh, I'll be presenting a case on functional materials for water purification for this online faculty development program on domestic and industrial water and wastewater treatment, which is organized by the Department of Chemical Engineering, BVRIT Institute of Technology in Medak, Telangana. So hello everyone. As already introduced by Dr. Srinivas, I am working as an assistant professor in chemical engineering department in BITS Pilani campus, Rajasthan. So the contents of my talk will be on functionalized materials and how this functionalized materials can be divided into two subclasses, that is functionalized adsorbents and functionalized membranes. A brief introduction about some of my research outputs and also some of the industrial consultancy works which I've carried out, which is in line with some of the which is in line with the domestic and industrial wastewater treatment. So coming into functional materials, it can broadly be divided into two subcategories. One is the adsorbents and the other is a membrane. So the objective of mainly making a functionalized adsorbent, we should keep in mind about the naturally amended materials which are abundantly available in different parts of our country. So those materials have a rich source of aluminum and iron. And if we are able to modify it chemically, we can use those materials in the removal of heavy metals and fluoride and other complex organic substances which persist in our aqueous environment. Finally, what we can do is once we had got hold of the removal mechanism and the removal type, we can go for pilot scale studies and ultimately scale it up. And when we scale it up, we can go for a field trial. And once we go for a field trial, we can assess the cost effectiveness of the material. And next, coming onto the membranes, there are different classes of membranes that we usually work upon. Some of them are nanofiltration, reverse osmosis membrane. But as you all know, nanofiltration or reverse osmosis membranes have their inherent disadvantages. So what are those disadvantages? The nanofiltration membranes have very small pores and thereby requires a lot of transmembrane pressure drop as well as energy cost in order to get itself operated. The same goes for reverse osmosis membrane. And in case of reverse osmosis filtration, what you have to do is you have to introduce something called mineralization technique so that the essential minerals from the domestic water or the industrial wastewater are not lost. Therefore, in order to curb this inherent disadvantages of a membrane, what researchers have nowadays over the last decade have devised a special class of composite membranes known as mixed matrix membrane. So in this kind of mixed matrix membrane, you impregnate a certain additive into a polymeric substance. And once these additives are impregnated, once these additives are impregnated, you can actually use it as an ultrafiltration membrane and therefore also exploit the adsorptive property. It can be used to remove arsenic, fluoride, and microbes, and as well as different properties of the membrane gets varied upon impregnation. There are different long-term studies as well, which needs to be carried out in order to scale up the performance of the BIM. So first, coming into the functionalized adsorbents. So functionalization is mainly carried out in two parts. One is a physical treatment part and the other one is a chemical treatment. In case of physical treatment, you usually burn out the adsorbent or the raw materials. The two types of process in which usually burning is carried out is pyrolysis and carbonization. Now, pyrolysis is a process where usually the raw material or the precursor is introduced into an oven and it is burned at high temperature in the order of 1000 to 2000 degrees Celsius in absence of oxygen. You can introduce some inert gases like argon or nitrogen in order to burn that substance. There is another process called carbonization, where the material is usually burned at a lower temperature, ranging from 100 degrees Celsius. And this carbonization is usually carried out in partial presence of oxygen. Once the physical treatment part is over, you can go for chemical treatment. And in chemical treatment part, you have two major processes, that is oxidation and reduction. Uh, Oxidation, as you all know, you need to have an agent which oxidizes the material. And similarly, in case of reduction, you need to have an agent which reduces the material to serve our purpose. Now, the factors in this kind of functionalizations are mainly two. What are those? Those are choice of precursor and the type of treatment process. Now, your precursor choice will ultimately depend upon your end use. So if you are trying to remove fluoride, which is a negatively charged material, you need to use a precursor which will have abundant positive charge on its surface. But on the other hand, if you are trying to remove a positively charged material, for example, say lead, you need to have a precursor which will have abundance in negative charges. So the choice of precursor is utmost important in this case, in this kind of functionalization process. The second is the type of treatment process. So based upon, again, the end user, what is your final application, you need to use the physical treatment part either in case of pyrolysis or carbonization, and also in chemical treatment you need to use oxidation or reduction. In most of the cases, what we see, what the adsorbents nowadays are prepared, the conventional adsorbents like activated carbon or natural zeolites or artificial zeolites, we carry out the process of carbonization because carbonization requires much lower temperature and thereby have much lower energy cost. And most of this material are oxidized and not reduced, because in case of reduction, somewhat the material behaves abruptly and doesn't have a good solid crystalline structure. So in our research work, what we had carried out, we used three kind of precursor: the natural laterite, bone meal, and iron ore slime. Now let me talk about these precursors. What are this type of precursors which are used? So laterite, as you all know, is red soil, is a rocky soil which are present abundantly in the plateau regions of India. So if you see in West Bengal, there is the Rar region in the Chotanagpur plateau. And if you see in the Deccan region, you have the Deccan plateau, where you have lots and lots of laterite as a rich source of iron and aluminum. So this is a type of soil. And if you use an activation process of a simple acid-based treatment, what is that? Firstly, you use an acid called hydrochloric acid, and then you reduce it by a base, that is sodium hydroxide. And therefore, what you will do is you will exploit the formation of iron oxyhydroxide or aluminum oxyhydroxide on the surface of this kind of natural laterite. Now, once you have this kind of activation process, the final product will be ready, and most of it are used in the application of lead and potentially toxic heavy metal removal. For example, cadmium, zinc, copper, and nickel. Secondly is kind of a precursor that we use called bone meal. Now, bone meal is a type of material which are used abundantly in phosphate fertilizer and usually a waste product. So once you use partial carbonization process, that is burn it at a temperature between 500 to 600 degrees Celsius in partial presence of oxygen. And then you use a treatment procedure of aluminum sulfate and calcium oxide treatment. Then you can get an end product which can be used for removal of fluoride and microbes. Finally, there is another type of precursor which is also a waste product called iron ore slime, which is a blast furnace waste. So it's a kind of a waste which is fed into the blast furnace to maintain the iron ratio, and this material is also a potential source of iron and aluminium. And if an activation process like natural laterite is followed, you can get a final product which can be used again for removal of arsenic and microbes. Now let us come into the different prospects or different research works which have been carried out with 3 different materials. So firstly, in preparation of treated laterite and iron ore slime, so the procedures that you usually follow is the sieving of the precursor. So if you can see my slide, this material which has which is a rocky soil, it's a hard ground, it's a hard granule. So what you need to do is you need to crush this material, and once you crush this material, you need to sieve it according to the type of sizes that you need. So once it suits your sizes, you have done your meshing and sieving, then you go for acid treatment. So acid treatment is usually carried out to have the presence of plenty of hydrogen ions on its surface. And now once this acid treatment is done, you perform a process of distillation of the acid treated mass so that the soil is not dissolved in it. So the excess acid is actually winded off from the solution. Now, once the excess acid is winded off from the solution, you do an hydrolysis, and therefore this hydrolysis is carried out by sodium hydroxide solution. So once the hydrolysis is carried out by sodium hydroxide solution, you have plenty sources of a superadsorbent on its surface, which are known as oxyhydroxide. And since iron and aluminum are abundant in its structure, therefore mostly iron and aluminum oxyhydroxides are bound to form on its surface. And now when you have treated it with an acid and an alkali, you need to do a water washing until the pH becomes neutral, and therefore no salt is left over. In case of carbonized bone meal and chemically treated carbonized bone meal, we first need to wash the precursor, which somewhat looks like this, whitish solid. And then similarly, we need to crush it and mesh and seal it. And when it is done, we will go for partial carbonization process. So once this partial carbonization process is done, you will find the end product as CBM. What is that? This is carbonized bone meal. Now, once this carbonized bone meal is obtained, you need to agitate it in calcium and aluminum dispersion in water. And I think Mr. Ashwini Kumar, you need to please put off your microphone. Yeah. So once this agitation is done, so once I finish my slides, then obviously I'll come to a question answer round. So please do not ask question in between. So once this carbonization part is over, we will go for agitation in calcium and aluminum dispersion in water. Now, the main reason for calcium and aluminum dispersion is the reason being calcium oxide or calcium hydroxide is obviously used as to provide reverse concentration gradient. Because whenever you add aluminum in water, it becomes very acidic. And therefore, whatever source of calcium is present within the bone meal, it might leach out. So in order to restrict the leaching out, we have to provide a reverse concentration gradient, and that is why calcium is used over here. And since aluminum also is a rich source of it up is one of a is one of an agent for uptaking fluoride, therefore aluminum sulfate solution needs, or any type of aluminum salt solution needs to be dispersed, so that this carbonized bone meal needs to be put in that water solution. Now once the agitation or the chemical treatment is done, we need to go for the drying, grinding, and finally sieving, and our end product will be CTBM, which is chemically treated carbonized bone. So coming into different characterization part which we had done for heavy metal removal, we can see from the SEM analysis that the surface more or less looks plain, while after treatment there are different cracks and pores which are developed on the surface. You can see from the property variation that the surface area initially for raw laterite, that is lateritic soil, was 17.5, whereas in treated laterite it increased comprehensively to around 75. In case of pore volume, there was also a successive increase, and the conductivity of the solution also increased nearly double time. So the main part over here is to look at the isoelectric point. The isoelectric point, that is the 0-point charge pH at 0-point charge, it was initially 7.4 for raw laterite, whereas in case of treated laterite, it was 6. Now there is a certain there is a certain theory to this portion. So if your pH, operating pH, is lesser than the isoelectric point, then the surface will become positive. And if it is more, then the surface will become negative. So as our treated laterite has a pH of 6, so if we operate at a pH of 7 or 7.5, which is usually the normal drinking water pH, our surface will become negative. And since our surface becomes negative, most of the heavy metals, for example, lead, cadmium, zinc, nickel, chromium, which are positively charged, will be attracted by the will be attracted by the adsorbent. And this part, what we see, leads to the basic conclusion, leads to the corroborating reason for this. For example, if you see the maximum absorption capacity for raw laterite, it was 2.7. Whereas after this treatment was done, the maximum absorption capacity increased to around 16. For cadmium, copper, zinc, and nickel, though it increased, but yet we were not able to find such comprehensive increase in this metal, in removal of this metal. But however, for the heavy metals, or especially for lead, this was more than 8 times increment in the absorption capacity factor. And thereby we looked into the X-ray diffraction characterization and other sorts of characterization as well. And this led to the basic conclusion of 2 schemes which can be concluded, or which can be theorified for the uptake mechanism of lead by treated laterite. So this is a structure of the adsorbent containing oxyhydroxides, and when lead hydroxide is put in a solution, it usually ionizes into lead and hydroxyl ions. So this lead gets exchanged with the oxyhydroxide bond, and it forms an intermediate structure in between, either in scheme 1 or as per in scheme 2. Now coming into the carbonized bone meal and chemically treated carbonized bone meal for fluoride removal. So the first thing that we did was optimization of the carbonization condition. So what we did was, initially we varied the heating temperature, and when the heating temperature was our main aim was actually to find out the fluoride uptake capacity and the BVRIT surface area. So if you see, once we increase the heating temperature from 300 to 550, 700, or 800 degrees Celsius, we saw a rough variation in the fluoride uptake capacity. Now, this was our major concern. So if we increase the fluoride uptake capacity, then we can fix that value of temperature. So in this case, if we go from 300 to 550 degrees Celsius, the uptake capacity was increasing from 1.2 to 8.3. But when we increased further to 700 or 800 degrees Celsius, it reduced. Now, what is the cause of this increment and what is the cause of this reduction? So in bone meal, we have a structure called calcium apatite. So this apatite structure is present in practically all the hydroxyapatite or apatite or in bone meal structures, and they remain in mainly amorphous form. Now, in order to make it more suitable for fluoride removal, you need to have a very shrewd form of a very crude form of a crystalline structure. So that crystalline structure will basically be present or will basically come into view once you increase the temperature. But if you further increase the temperature to a higher state, it will turn itself down to ash. And once it turns itself down to ash, we will have a reduction in the fluoride uptake capacity. This can be corroborated by the BVRIT surface area. So you can see from 75, it increased to 97. And once we increase the temperature to 800 or 700, it reduced down. Now, once we fix the temperature at 550, because at 550 degrees Celsius, our maximum surface area and the uptake capacity was coming. So we fixed the temperature at 550, and thereby we then went to optimize the heating time. So we saw that once the heating time was also increased, it was increased from 550, say 2 hours, we were getting 5 milligram per gram of uptake capacity. Now, when it increased to 4 hours, we got 12.5. Now, what is the reason for this? More uptake, more increase in heating time will lead to the preparation of more supercrystalline structure. But again, there is a certain bar to it. If you go beyond a certain time scale, it will again turn itself down, or a part will turn itself down to ash. So therefore, once we exceeded this 4 hours and went to 6 hours, it decreased to 8.3. Now, the yield percentage is basically, if you have a raw material, what is the output that is coming out? So 74% of the raw material we were getting as an output. But as it is the case, so if you increase the temperature, therefore you will get less amount of yield percentage. Now, from 74, it reduced to 66. This is obvious, because as the temperature increase, there will be a part which will be which will be getting transformed into carbon, or which will be getting transformed into gaseous products, and it will not remain in the solid state. So after all the experimentation were done, we were able to conclude that heating temperature of 550 degrees Celsius and a heating time of 4 hours and a heating rate of 60 degrees Celsius per minute were able to achieve a fluoride uptake capacity of 12.5 milligram per gram with a yield percentage of 61% and a surface area of 110 meters square per gram. Now, this was our final material from the partial carbonization process. So as we went from, as we were able to make this one, so then we went on to the uptake capacity variation with chemical treatment. So how did we do that? So first of all, we have aluminum sulfate dosage variation. So when the dosage was increased from 100 to around 500, and the captive capacity was also increased to 102. Now at 500, we were seeing this part is nearly getting saturated. This calcium oxide dosage was kept fixed, but then when we got at 500 gram per liter of aluminum sulfate dosage, we fixed it at 500 and then went for calcium oxide dosage variation. And finally, we were able to achieve uptake capacity of 150 milligram per gram. Now, this 150 milligram per gram is the highest based capacity for for any type of natural adsorbents which are present for fluoride removal. Now, as aluminum was present in the crystalline structure, we were able to see that by the antimicrobial study that it was also able to treat E. coli cells. So the upper SEM figures represents the E. coli cells. The first one represents the sole bacteria. While when it is treated with carbonized bone meal, there was a reduction in the green dots, as well as there was a rupture in the E. coli cells. Now this represented that the CBM, that is the carbonized bone meal, were able to treat bacteria successfully. Now, when we used chemically treated carbonized bone meal, the number of green dots, that is bacteria, which is obtained by the optical microscopic image, were still reduced. And we can also see there are few pores over here, there are few voids over here, and this represents the died bacterial cells. So chemically treated carbonized bone meal were able to treat the bacterial cells as well. Now, coming from the SEM and the TEM analysis, when this represents a merely clean structure, an amorphous structure, whereas after treatment there are deposits of aluminum and calcium over its surface. And from the transmission electron microscopic structure, we were able to see there are rods, aluminum rod-like structures inside the pores of chemically treated carbonized bone meal. And based upon the lattice fringes that we obtained, we were able to say that we had a good scope of impregnation within the material. Now, after this characterization study and the batch studies were done, we did a sort of fixed bed column scale analysis. And when we did this fixed bed column analysis, we ran it at different operating conditions. And we varied the operating condition based upon bed height, the inlet concentration, and the flow rate. And once we got this, we used a simple number of bed volume method to scale up the material and which will be able to predict what amount of material will be used or what amount of total adsorbent weight will be used for having a filter life which will have an efficiency like 1800 days or 2000 days or more than that. And this was basically varied with the number of liters that you produce in a day. So obviously your flow rate will have a significant impact on the efficiency of your process. So two types of analysis were done. The first analysis was for removal of fluoride by chemically treated bone meal, carbonized bone meal and chemically treated carbonized bone meal. And the second analysis was removal of heavy metals by treated laterite. So this two structure, the first one you can obviously understand. So point A represents a filter with 40 centimeter height and 20 centimeter dia. So if you see this material and it is having a 44 liters per day, if you predict, then for having an efficiency of say 250 days, an amount of 25 kgs will be required. So if you see for 150 kgs, for having for say for example G, the point G is 100 centimeter height and 20 centimeter dia. So 150 kg material will have a filter life days of around 1200. So basically around 4 years. Similarly, we can do the same thing for lead removal as well. And once the main studies were done, we used our data in fabricating a filter, which has I'll come into the filter structure later. So we were able to make a fluoride filter, and we installed it in one of the acute fluoride infected area in one of the region in West Bengal, where I was doing my PhD in IIT Kharagpur. And it is still running as of now. Now the main question is this data what you have obtained from scale-up studies will actually not confirm with the one that you have obtained, that you are basically obtaining from the real life performance. The reason being, in the scale-up studies you were using anti-gravity flow. That is, you were pumping the fluid solution from bottom to top. It was using the full bed. So it was it was a worst case performance. Now in case of this fluoride filter, it was a situation where we were using the solution to run with the gravity, that is from top to bottom. So once we use that, it will not use the full bed, and therefore it is one of the best possible cases, and hence your filter will run for more amount of days. So we found it by experimentation that usually the data which we got over here it actually varies around between 20 to 30% of the normal values that we get from the scale-up studies. Now we did a cost prediction calculation. So finally the cost price of the material was around 30 rupees. So this is the cost which was incurred for buying the bone meal from the suppliers. If this can be reduced during bulk production, if there is a mutual understanding between the bone meal suppliers and the animal husbandry department. Now, if we use the electricity cost, if we calculate the electricity cost during carbonization, so if we assume that 2 kg of materials can be inserted to a furnace, which has a rating of 2 kilowatt hour. So the total time of carbonization is 4 hours, and therefore the energy consumption is 8 kilowatts. And usually, if we assume that the cost of electricity per units of kilowatt is 8 rupees, this is the source being West Bengal State Electricity Board. So in most of the industry in India, across India, it varies from 8 to 10 rupees. So the cost of electricity for carbonizing 2 kgs of bone meal is 64 Indian currency. And therefore the cost of electricity per unit will therefore be 64 divided by 2, and therefore 32 rupees. So 32 rupees is incurred in carbonizing 1 kg material. Now for chemical treatment part, so if you see the chemical treatment part, you have 1 kg of carbonized bone meal, then 5 kg of aluminum sulfate and 0.2 kgs of or 200 grams of calcium oxide is used. So cost of aluminum sulfate if per kg is 10 rupees, and that of calcium sulfate is around 4.5 rupees. The source being India Mart, from where we bought this material, and therefore the total cost due to this chemical treatment will be 51 Indian currency. Now the cost of drying we used as 8 rupees, and overhead cost we assumed 10% of the total items. That is sum of cost price, electricity cost, and chemical treatment and drying cost. And it came to roughly around 12.1. Therefore, the net cost for preparing 1 kg of adsorbent is 133.1, which is roughly 133. That is $2. Now, this is the material cost. Now, once we have this material cost in our hand, then we will be able to actually predict what will be the cost of the total filter. So the filter will be made of this filter body, the different pipelines, the buckets. You will have other materials as well in addition to the material that you are using for fluoride removal. And we did a cost comparison with different type of filters which are available in the market and which claims to remove arsenic and fluoride. So the first one being Envo iron arsenic fluoride filter, containing activated alumina and activated charcoal, and the purchase cost is roughly around 40,000 rupees. For Kent Supreme RO water purifier, it is around 20,000. For Berkeley Light, it is 17. For Ultra Pure, it is 25,000. For Aquacera HCS, it's 14,000, roughly around 15,000. And Blue Water, it is roughly coming to be around 2,92,000. So if we use this indigenously developed fluoride and microbe removal filter, the total cost will come around 3,800, which is roughly one magnitude time lesser, 10 times or 100 times lesser than most of the conventional filters which are used in our market. And now for after 2 and 3 years, when the material gets exhausted, so we need to have a proper regeneration protocol for that. And once we can regenerate it, it will again run for 2 or 3 years. And finally, the maintenance cost for this regeneration will be coming around 600 rupees. So this is the part for the functionalized adsorbents. Next, we come into functionalized membranes. So this functionalization of membranes are usually carried in 4 ways: the solvent exchange method, surface coating, chemical treatment, and annealing. So I feel all of you know about this type of process while you functionalize a membrane. But the factors over here which should actually empower us to choose one amongst this functionalization technique is the selectivity and the productivity. Now, the selectivity was, what is the selectivity? That is what type of contaminant you are removing from the domestic or the industrial wastewater, and what is the total amount of flux, or what is the flux that you are, or what is the amount of pure water that the membrane is producing. Now, in our case, the details of research, we fixed the solvent because it was the mostly available solvent in the market, that is dimethyl formamide. And we used all types of biocompatible polymers in this case. So biocompatible polymers doesn't have any acute toxicity with the human cells, or it doesn't produce any byproducts. So most of these are cellulose acetate phthalate, polysulfone, polyacrylonitrile. And in this case, we used additive to increase the pore size and to add extra mechanical strength to the membrane. Mostly these additives were polyethylene glycol and polyvinyl pyrrolidone. And the inorganics that we used for fabricating these mixed organics membranes were many. So for DMF and cellulose acetate phthalate, we used inorganic called activated alumina. For DMF and PSF, we used carbonized bone meal. For DMF and PAN, we used treated laterite. And for DMF and PSF, we used treated iron ore slime. So the geometries were also varied. The first one was flat sheet. The second one was hollow fiber. And the third one was again a flat sheet, and the fourth one being again a hollow fiber. And we used it mainly for fluoride and arsenic removal. So how do we prepare these hollow fibers actually? So usually how these membranes are prepared is you first preheat the polymer and the additive in the solvent. And once the preheated solvent, preheated polymer or additive is being dispersed in the solvent, then you sonicate the organics in the solvent and then agitate the two mixture thoroughly so that well dispersed homogenized solution is produced. Now, once you have the well dispersed homogenized solution, you can cast or spin the solution. And once it gets casted or spent, you can inverse the phases in a gelation or spinning bath and finally produce a flat sheet or a hollow fiber membrane. Now, in this case, I will go through the method by which these hollow fibers are produced. So you have a polymer tank and a bold liquid tank. Someone is actually scratching on this slides. So please do rub this. Please do not scratch anything on the slides, please. Okay, so you have a polymer tank and a bold liquid tank, and you will need to have a needle assembly. In the needle assembly, you will have a polymer which runs from the outer end, and a bold liquid which is mainly water will run from the lower end, and thereby it will give you a hollow fiber of this sort. There are different effects of sonication time on different membrane properties as well. The first being the molecular weight cutoff, the porosity and the permeability. So the molecular weight cutoff, when you have proper dispersed phase of inorganics in the solution, the molecular weight cutoff will reduce. And now when the molecular weight cutoff is reduced, what happens is your pore radius will reduce. And that is also a very significant impact on the type of membrane that you are using. If the pore size of the membranes get reduced, it will be able to actually deposit on its surface a different type of materials which have higher sizes than the pore size. So by sieving mechanism, it will be able to restrict the entry of different type of other contaminants which it is not able to remove by adsorptive property. Now, there are other factors as well which significantly gets increased, the porosity and the permeability. So the porosity gets increased from say 10% to around say 40%, and the permeability, that is which is a measure of the productivity of the membrane, it gets increased to 1 to 1.5. And therefore casting time or the sonication time has a profound effect on the functionalization of the membrane. There are other surface properties as well which gets hampered or which get significantly impacted by the dissolution of inorganics within the membrane. So a SEM analysis is prepared in this case. So mainly in phase inversion method, there are two types of process which is done. Mainly two types of process is there by which these membranes are formed. One is known as a delayed demixing and the other one is known as instantaneous demixing. So when you put the polymer solution in a gelation bath which contains a non-solvent like water, there will be a demixing process. That is, the solvent will go out and the water will rush in. And this demixing process helps in giving rise to different type of membrane morphologies. So if you have a delayed demixing, that is the solvent and the non-solvent exchange is taking place at a lower rate, then you will have a macrovoid formation, which is somewhat like this. But when you have an instantaneous demixing, you will have pore-like structure, which is like this. So therefore, in this case, what we learned that across the cross-section of the membrane, there is a delayed demixing process. And because of this delayed demixing process, this macrovoid structure, which were initially elongated in length, it increased its length while it reduced its breadth, and therefore the number of macrovoids were also reduced. But on the top surface, we were able to see that once the additive concentration increased, the instantaneous demixing were restricted, and therefore the top pores were restricted with the continuity of this top pores were restricted with different type of inorganics that we were impregnating in the membrane. The second analysis was AFM analysis, that is atomic force microscopic analysis, which we were able to see, or which we were able to justify with the uptake of contaminants. So smooth surface will not be able to uptake more contaminants from the surface. And therefore a rough surface will be able to uptake a lot of contaminants by adsorptive measures. So in this case, AFM analysis were done, and we were able to see that once we increase the concentration of inorganics, once we increase the concentration of inorganics in the membrane, the surface roughness were increased. From the XRD analysis, we were able to conclude that in a pure membrane, we had different peaks of sulfone and polyvinyl pyrrolidone, that is mainly the polymer and the additive which we were giving. And there are different peaks, there are different structures or mineral phases of the inorganics which we impregnated. And both these components gets adhered, or both these components were present in the final crystalline structure of the mixed matrix membrane. The FTIR analysis, we were able to detect different types of functional groups which were present, and this peaks get subdued before and after the adsorption of arsenic or fluoride, which were our solute in this case, because the transmittance were reduced once this solute gets adsorbed onto the pore surface. Now, different inherent properties were also significantly impacted. One of these were the porosity and permeability. Now, as we discussed on the SEM image, the continuity of the pores gets decreased. And since the continuity of the pores get decreased, we have a severe reduction in porosity and the permeability of the membrane. Now, this is one of the most important drawback of this kind of membranes where we are preparing. So there effectively, we need to strike a balance between our selectivity and the productivity when we are trying to fabricate this type of membranes. Because obviously, when your top pores or the macrovoids gets reduced in length, you will have a decrease in the porosity and the permeability. Now, the second one which gets effectively reduced is the molecular weight cutoff. As I was saying, once you increase the quantity of inorganic additives, your molecular weight cutoff will reduce, and hence the pore radius. But most significantly, what will get reduced or is the contact angle. And as the contact angle gets reduced, Therefore, once the contact angle gets reduced, it means that the membrane becomes more and more hydrophilic. Now, there is an important conclusion in this case. So you might be thinking that the permeability is getting reduced, whereas the hydrophilicity of the membrane is getting increased by the reduction in contact angle. How is that so? So am I speaking a lie? Now, that is not the case. So in this case, if the permeability gets reduced, that is due to the discontinuity of pores or the blocking of pores on the top surface of the membrane. Whereas when the phase inversion is taking place, the hydrophilic inorganics which we are impregnating in the membrane usually comes up to the top surface, and these are water loving agents. So when it comes to the top surface, this attracts more and more water, but the pores are getting reduced. So the pores are getting reduced, but this hydrophilic additives are coming onto the top surface, and therefore it is attracting more and more water. Therefore, the hydrophilicity of the membrane gets increased in this way. There is also success means a successive reduction in the surface area variation. From the regeneration, we were able to see that mostly the adsorbed and the desorbed percentages roughly varied by the same amount after around 5 cycles. So I'll just try to give a quick briefing about the long run that we had done, that is a dynamic cycle which we had experimented in our lab, and it was for more than 28 hours or 30 hours for a membrane having an area of 0.01 meter square, which is quite small. And we were able to see that for the first initial case, it was able to filter a water of 1400 cc. And for the second case, it was around 1200 cc. And for the third case, it was around 1000 cc. The feed was 5 milligram per liter, that is 5 ppm. The pressure was 34 kilopascal and the cross flow rate was 10 liter per hour. So different other water parameters variation were also studied. And along with fluoride, we were able to see that microbial reduction were also done, because there is a lot of iron containment, or there is a lot of iron or aluminum containment in the CBM structure. And essential minerals and essential salts are also retained, unlike reverse osmosis. We were also we also achieved successful result in when we used polysulfone and treated iron ore slime mixed matrix membrane, and we were able to see that for a time of roughly around 26 to 28 hours, the breakthrough time was achieved for this kind of membrane. And also along with the arsenic, iron was also reduced, and the microbial count from both the most probable number method and the colony forming units method, the amount was also reduced in the final permeate solvent, in the final permeate. So this shows a rough bacterial rejection profile for a cap alumina mixed matrix membrane, and for an efficient time of around 3 hours, the rejection was roughly around 100%, and it continued for the final time, for the final amount of time which we used for dynamic filtration. So these are some of the international journal publications which are there under my belt. And coming into the filter which we had fabricated. So this is the outer body of the filter. So if you look at this picture at the top part, we given water which contains fluoride containing a solution from the tap. Now, when we place this water over this top, and this is a household filter, you can also get it for community scale as well by just connecting this knob with a source of entry of water. And now this goes with the gravity along this filter body, and the filtered water is collected from the bottom. Now, the different materials which are there in this filter is, first one is the raw laterite. So raw laterite usually decreases the concentration of fluoride or arsenic, which will be directly hitting our main adsorbents over here, followed by a bed of treated laterite, which will also reduce the concentration of arsenic and fluoride or different heavy metals which are present. Activated charcoal will reduce the concentration of smelling agents, for example, sulfate or phosphate, if there are any in the if there are any in the feed water stream. There will also be an extra bed for bacteriostatic carbon, even though carbonized bone meal and chemically treated carbonized bone meal along with treated laterite acts as antibacterial agent, but still, to be on the safe side, we give a layer of bacteriostatic carbon, followed by sand, which efficiently removes any type of turbid factors or any type of small particulate factors which are otherwise not removed by this raw laterite layer. And finally, we give a distributor plate at the bottom so that all the distribution channels can be effectively combined into one outlet and it flows into this bucket. So there are different types of community scale filters as well, which my supervisor along with me had installed in different parts of acute fluoride and arsenic infected areas in West Bengal. So this is one of a school in Bankura district in West Bengal. And this is also one of a school which is in the Birbhum district of West Bengal, where we had along with one startup agency had installed this type of filters for the beneficial for benefiting the school students, for helping those poor little kids to drink safe, to have access to safe drinking water. So a rough estimate of my industrial consultancy, although Professor Srinivas has given a quick review of that. So I was working as a senior engineer in Tech Mahindra Technology Center in Hyderabad, where I was offering consultancy to GE Appliances. And in GE Appliances, I was entrusted with the work of formulation of next-gen water filters, sensor fabrication, leak detection, and aesthetic handles. I was also giving consultancy to PepsiCo, and this was for the techno-commercial recommendations for installation of an inline device which can detect starch from potato water washing in a chips producing unit. Mainly, PepsiCo produces Lay's, and in Lay's, when they use potatoes in the first instance, they wash those potatoes, and when these potatoes are washed at a high jet speed of water, there's a lot of starch which comes out from the potatoes, and they need to install inline refractometer in that column which can detect the quantity of starch that is actually leaving from that stream, so that they can recover those starch and use it in different other applications, like making some candies or making some toffees for kids or even for adults like us. So the third consultancy was provided to Procter and Gamble. Mainly all of you probably use Head and Shoulders. So Head and Shoulders is manufactured by Procter and Gamble, P&G. So we are still working on this. It's for the formulation of highly specialized surfactant, which can instantaneously wash off any type of stains in a garment. And therefore, we do not need to use the washing machine, or we do not use to use excess water for rubbing it off. And in Filtrex Technologies, after Tech Mahindra, I joined there as a senior scientist, and I was providing consultancy to KX Technologies, which were under Marmon Waters. And we had developed a patent on the removal of arsenic through a zinc nanoparticle, which will be there in a carbon matrix, and that can be installed in a filter. And this consultancy was actually a joint venture of KX Technologies and Kent RO in India, and Graver Technologies as well, where we need to prepare different specialized metal organic frameworks for removal of volatile organics from water. So these are some of the prototypes which are developed during my industrial stint. So the first one is a lead detection prototype. So I better will start a video in this case so that it is easier for you to understand. I hope everyone is able to see this video, or there is some problem in sharing. Is everyone able to see this video? Okay. Converts the analog reading of the Arduino board to voltage by this equation, and later it converts the voltage to concentration with the help of this calibrated voltage. This is the basic prototype over here, which we have. This prototyping can be further extended by changing the quality of the electrodes, changing the quality of the copper wires, structure of the beads, and also distance between the electrodes. This can be modified to a great extent, but this is the basic structure of making detection assembly. So in case everyone wants to know about how this type of beads are produced by phase inversion technique, so this is again a small video for the same, how we were able to actually prepare these beads. So you have a polymeric solution from the top, and you have an injection syringe module by which this polymeric solution were filling at the bottom of a solution which contains water along with an amine base solution. So now when it drops into the solution, and therefore this turns into this globular like structure like this. And these are polymeric beads which can be used for varieties of application. In fact, in my stint with Techem, when I was offering consultancy with GE appliances, these beads were used for lead detection as well as for polymeric sensors. The other prototypes which we used, which we were able to fabricate, and those were trade secret of this enterprises, aesthetic handles and leak detection using conductive primer. So these are both patented by GE appliances, and these aesthetic handles are not in line with this faculty development program, but still I'd like to actually share a couple of things with you. A brief thing. So everyone knows about Briggs-Rochet reaction, which actually is known as trophic light reaction. So when you use a dye along with a alkali in a glucose-based solution, and you agitate the solution, it will actually change its reaction from it will actually change its color from red to green, and in between it will be transforming to an indigo based solution. So whenever a user actually comes in front of the door panel and tries to open the door, there will be agitation of the mixture, and it will change its color, and therefore while doing a monotonous job, it will provide an aesthetic factor enhancement factors to the user, and therefore the selling of this kind of handles will be greatly be fastened. And finally, we were also able to actually develop a leak detection manual using a conductive primer. So whenever anything falls on this circuit made up of this conductive primer, the structure will glow and therefore will enable the user or the service provider to know that there is some leakage in across the refrigerators or across any type of devices what you are using. So thank you everyone for this wonderful session organized by BVRIT. It's being a very informative session, and I greatly do acknowledge to all for giving me a opportunity to speak in this forum. Now I am open to take any questions that uh, you will likely to share with me, or you likely to have you likely to put in front of me. Okay, the video is not able to see. Okay, just a minute. So this is how a polymeric solution actually is coming onto so this is how beads are prepared actually. So a polymeric solution is phase inversed in a gelation bath. So this falls in a gelation bath, and therefore it is being modified onto a jelly-like state to a solid-like state over here. And these beads are finally used in making lead detection assembly. So now you're able to see. Okay. So now let me again show you the bead assembly over here. So these beads are used for lead detection as well. This is the lead detection assembly. This entire portion contains the beads, graphite electrode, copper electrode. This is a stand practically used for building this entire setup in bead. This wire leading from the graphite electrode is connected to the A0 port of an Arduino, and wire from copper electrode is grounded. That is connected to the ground port. Now the beads are getting immersed in water. Wait for some moments. Run the Arduino program. converts the analog reading of the Arduino board to voltage by this equation, and later it converts the voltage to concentration with the help of this calibrating equation. This is the basic prototype over here, which we had. This prototyping can be further extended by changing the quality of the electrodes, changing the quality of the copper wires, structure of the beads, and also distance between the electrodes. This can be modified to a great extent, but this is the basic structure of making detection assembly. This is the lead detection assembly that we are talking about. This. Okay, so I believe now everybody has seen this. So now I am eager to take up questions. So the first, I think, is from Moti Krishna Mohan. So yeah, we have almost all the facilities in our lab. Now I am trying to develop all these facilities over here. So initially these were at TechM and IIT Kharagpur. When TechM I was doing my post PhD work over there, and in IIT Kharagpur my PhD. So all those were there. Yes, I'm trying to I'm developing all those facilities over here. I've got some grants from BITS Pilani, and therefore those structures or those equipments which I had worked upon during my PhD tenure will be used over here. The next being Subhadeep Jana is, yeah, we will share slide, but that depends upon the organizing committee. I do not have anything to say over here. Yeah, this process is suitable for removal of fluoride in effluent as well. So you can use this chemically treated bone meal or chemically treated carbonized bone meal for removal of fluoride in different types of effluent. So we are now actually on the starting point of using different textile effluents which might contain fluoride, and how to convert those effluent into potable drinking water. So my question is that whatever the chemicals we are using for treatment, does they have any negative impact on human health if we consume that treated water? So see, when you are using any chemicals for treating any adsorbent, you have to make sure about what are the things that are leaching from that adsorbent. So we had studied the leaching efficiency, and we saw that the leaching percentage is very negligible, and if we consume that water, that is absolutely safe for human health. What process you are talking about means which what process and what limitation? Anyhow, limitations in this process. So which limitations you are talking about, Mr. Jana? So I do not actually understand which process you are talking about. Is it the adsorbent process or is it the membrane-based process? We can consider a biological method of treatment. We can consider, but the main problem with biological method is the equilibrium time or the treatment time is very small, and means it will only be applicable to very microscopic scale. So if you want to treat waters, usually in industrial based treatment or domestic water treatment, you will have to treat gallons of water in a day. So under those circumstances, I don't know how biological method will perform. Yeah. TDS is around 200 ppm. So the safe limit of TDS you'll have to see. So if the TDS it's around 200, if it is around 600 or 1000 ppm, it will be able to remove those TDS as well, because we are giving an extra layer of activated carbon and sand, and it will be able to remove that TDS as well to uh, to roughly around 50 or 80. Well, which among the two processes, membrane and adsorbent, is most common effective, is most cost effective? So obviously, adsorbent process is cost effective process, but membrane based process actually gives you a lot more options to exercise. So you need to have a hybrid technology for this too as well. Okay, the next one is when we are doing adsorption for removal of arsenic, the adsorbent that we use will have heavy metals, arsenic, which is very dangerous for human. So what is the best solution for that? So I didn't understood this question. So the adsorbent doesn't have any heavy metals actually. So the adsorbent removes heavy metal. Arsenic will be removed by this adsorbent along with the other heavy metals that potentially coexists along with arsenic in domestic or industrial wastewater. So what is the main objective behind acidic treatment? The main objective behind acidic treatment is to introduce hydrogen groups onto the surface of this adsorbent, so that the basic mechanism is you have a structure called hydroxide. So when these hydroxides are not being able to remove the heavy metals or arsenic from water, so now you potentially need to oxidize it to oxyhydroxide. And in order to oxidize it, you need to first do an acid distillation of the mass. But you need to keep in mind that while doing acid distillation, the entire mass doesn't get dissolved. So therefore, you need to remove the excess acid as well. So there is another question is once we do chemical treatment, just you said for increasing temperature for fluoride removal, does it impact the microbial diversity which are used for biological treatment? Absolutely not. The physical treatment is mainly the one where we are increasing this temperature for fluoride removal, where we are increasing this temperature for making the adsorbents for fluoride removal. There is no question for impacting the microbial diversity. So the next question is, when we are removing arsenic using adsorption, means arsenic will be present in the adsorbent. So after removal, okay. Now this is a very important question which Mr. Naga Saujanya has asked. So now every adsorbent has this kind of thing. So what after, or what is the aftermath of this adsorbent when it's exhausted? What we will do with that? So basically, what we had started with treated laterite. So there is something called toxicity characteristic leaching protocol, TCLP. So you can search it in the net, or you can go in the textbook of Metcalfe and Eddies. What is TCLP? So in TCLP protocol, you need to study about the different toxic metal leaching or toxic element leaching, and will that affect the aqueous environment as well? So we carried out TCLP with treated laterite and bone meal adsorbent, and we found out that there is no actually leaching of harmful metals from those adsorbent, which is above the permissible limits. So now what we need to do with this adsorbent is that, since laterite is a soil structure, so we can use it for road laying purpose. And since bone meal is converted to chemically treated carbonized bone meal, and partially carbonized bone meal as well, so we can use this two adsorbent to make a fuel we can use this as a domestic fuel, and we can charge it with coal, so that we can use it for a domestic fuel, and And fluoride being a very light element, even if it dissolves out into the atmosphere, we can use a scrubber like structure before, and we can restrict its actually dissolution in the outer scale. So that's something that we are doing. So but as of now, there is no thesis or postulate which is coming out of that. But yes, we can use it for road laying, as well as we can use it for as a domestic fuel. So can you illustrate the role of chlorine in treatment of water? Yeah, chlorine is used as a disinfectant in water treatment. So that's some of the common role that we usually assess with. Okay, sure. I'll make you the host now. So I had made you the host, I believe.
Sir, thank you, sir. Thank you for your wonderful, nice lecture, and it was very informative. And for most of the young fellows like us, we are in the process of wastewater treatment, but a lot of problems, a lot of difficulties are there. So, based on your presentation, we have gained a little bit knowledge, sir. Thank you for wonderful section, sir. As a short notice, you have accepted, and I have given a wonderful presentation. Thank you, sir. Thanks a lot. Mute అయిపోయింది. Unmute. So,
Yeah, thank you, Dr. Srinivas, for actually giving me an opportunity to speak over here, and it's been a wonderful experience. And I feel a lot more of this kind of webinars and should be arranged by your college so that different type of collaboration opportunities can come up to the surface between different universities and India, and we can cope up with different types of water-based problems, or even different other problems that rises in our country, and especially give a solution to this kind of emergency situation through which our country is going through now. Thank you very much.
thank you, sir. Thank you. Thanks a lot.
Thank you.